Alright, building limits from the ground up, which means starting from definitions. And the definition that we're going to give is the epsilon-delta definition of the limit in the one-dimensional scenario. Meaning we're going to consider functions of a single real number input that give a single real number as the output. So what I mean when I say that the limit as x approaches a of some function f of x equals L is that for every real number epsilon you can imagine that's greater than 0, there exists some other real number delta which is greater than 0, such that if you guarantee to me that x is within delta of a, then you have also guaranteed to me that f of x is within epsilon of L. Now these are some fancy symbols and some fancy math speak for a very simple and intuitive concept that we can squeeze f of x to being arbitrarily close to L, which is what this epsilon is supposed to represent, by squeezing x to being closer and closer to a, which is what this delta is supposed to represent. And to consider an example, let's consider a function f of x equals x squared over x. Now it's tempting to immediately simplify this to x, which is true everywhere except for a single place, when x is equal to 0, because in that case we get 0 over 0 in our function, and this is bad. Now if we plot our function, right, always make sure to label your axes. For every real number, for every positive real number, you'll see that f of x really is just x. For every negative real number, f of x is equal to that as well. And the only problem that we get is right here at x equals 0. But the point of limits isn't for us to evaluate bad terms like 0 over 0, but they're a tool for us to reason about how this function is behaving as x gets really, really close to 0 from either side. For example, if I want to say, what do I need in order to guarantee that f of x is never more than 1 away from 0? In other words, that it's never greater than 1 and it's never smaller than negative 1. How do I need to constrict the possible values of x in order to make this happen? Well, because this function is so simple, we know immediately that squeezing x to being between negative 1 and 1 gives us our desired result. If we instead want f of x to be always within 0.5 of 0, let's say, we can squeeze x to being within 0.5 of 0. And this lets us, what this really lets us do is this lets us talk about arbitrarily small values. Since if we want to talk about squeezing and how f of x is getting closer and closer to 0, what we really want to be able to prove to someone is that give me any arbitrarily small value of epsilon you want. Maybe it's a half, maybe it's 0.0, maybe it's 0.000000, you know, lots more zeros, and finally a 0, 1. You want it to be not more than this much away from 0. Well, I can tell you a delta, and all you have to do is make sure x never strays more than delta away from a, and I can guarantee you that your function will never go more than this far away from your desired limit value, or whatever the true limiting value is. So this function, this definition, all it's really doing is putting an intuitive idea, a guarantee that we would actually want, and translating that into formal mathematical symbols. And using this definition lets us prove some really nice and also fairly intuitive properties of limits. One of which also has a way of being stated that rolls off the tongue pretty nicely, that the limit of a sum is the sum of the limits. And more precisely, this means if we have two functions, f and g, and we know beforehand that the limit as x goes to a of f of x is some number L, and the limit as x goes to a of g of x is some number m, then if I were to consider the sum of these two functions, if I were to consider the sum of the two functions and take the limit of that as x goes to a, then the answer I'm going to get, one, it exists, and it's also just equal to the sum of the individual limits. And we can actually use the epsilon-delta definition to prove this. So let's start by writing exactly what we're saying. For every epsilon that you could imagine, and of course this includes arbitrarily small values of epsilon, we need to show that there exists some delta greater than 0 such that whenever I squeeze x to being within delta of a, I have also squeezed the sum f of x plus g of x to being within epsilon of the sum of L and M. Alright, so the first thing that we're going to do is we are going to rearrange the terms in that final absolute value. So let's rewrite it f of x plus g of x. We're going to discard the parentheses in the starting terms, but we're going to keep them here. Now let's group the functions with their respective limits. So we're going to group f of x minus L in one term, and we're going to group g of x minus m in another term. Okay? Now, by the triangle inequality, we know that we are allowed to... this absolute value starter does not belong here, though it does belong in the next step. So as I was saying, by the triangle inequality, we can actually split this absolute value into the sum of two individual ones, so long as we add the caveat that these two aren't necessarily equal, but that this is going to be greater than or equal to that. F of x minus L in its own absolute value plus g of x minus m in its own absolute value. And this is the triangle inequality. Now the reason we wanted to do this is because we do have guarantees about the behavior of these two terms. Because we were told from the outset that this limit exists and is equal to L, and that that limit exists and is equal to M. So let's say that I want to squeeze the sum using some value epsilon. Maybe it's 1, maybe it's a half, maybe it's 0.1. Take epsilon and cut it in half. So what we're really interested in is epsilon over 2. We know that for epsilon over 2, there has to exist some delta f, which is greater than 0, some real number delta f, which has the property that if I were to squeeze x minus a to being smaller than delta f, then I have guaranteed that f of x minus L in absolute value must be smaller than epsilon over 2. Now, that's because the existence of this limit guarantees to me that this works for any epsilon I can imagine. So first I'm going to imagine some value epsilon, and I'm going to cut that in half. And you'll see why in just a moment. I'm going to cut that in half, but that's still a real number that's greater than 0. And so there has to exist some delta that lets me squeeze this function to being that close to L just by squeezing x to being within delta distance of a. Similarly, there has to also exist g, some delta g for the same reason, because this limit up here exists. So we can squeeze x minus a to being smaller than delta g, and what that will guarantee us is that g of x minus m is smaller than epsilon over 2. And the final step that's going to bring all of this together is we're now going to choose a value that's going to work. We're going to choose the delta that we need to exist from here. We're going to choose that delta to be the minimum of these two. And what does that do for us? Well, suppose I do provide the guarantee that x minus a is smaller than delta. Well, since delta is the minimum of these two deltas, x minus a is simultaneously smaller than delta f and delta g, which means that both of these guarantees are simultaneously provided to us. So f of x minus L plus g of x minus m inside their own respective absolute values is smaller than the sum of everything on the right-hand side, epsilon. But remember from up here that because this is always greater than or equal to that, and the transitivity of these inequality operators, epsilon is ultimately greater than this term right here. So we have f of x minus L plus g of x minus m. And this time we've grouped both of these expressions under the same absolute value sign. All of that is smaller than epsilon. But this is nothing but a rearranging of this term right up here, which is the thing that we needed to prove. And so we've finished our proof, guaranteeing x minus a to being smaller than this delta which we've chosen using values which are guaranteed to exist, ultimately guarantees to us that we have properly squeezed our function using whatever epsilon we want.